Welcome to today's webinar. I'm Michael Pfeiffer from Industrial Metallurgist, and today the guest speaker is Danny Schaeffler. He'll be talking about Introduction to Sheet Metal Formability. He'll be talking for about 30 minutes, maybe a little bit more, and then afterwards will be time for questions. And if you have questions along the way, just type into the chat box and we'll see if we can answer them along the way or just answer them at the end of the session. So with that, I'll let Danny take it away.
Very good. Good morning, everybody. Let's see. All right. The screen looks clean. I love it. Good morning, everybody. Welcome to today's speedy webinar. We're going to try to keep it as speedy as possible. My name is Danny Schaeffler. I'm president of Engineering Quality Solutions, and I do want to thank Mike at Industrial Metallurgist for the opportunity to speak to this crowd. My background, I spent 10 years with LTV Steel in the late 90s up until 2001, when LTV filed for Chapter 11, giving myself and 15,000 of my closest friends the opportunity to pursue other interests. And I formed Engineering Quality Solutions, a metal formability consulting firm. And not only do we work on trying to solve in-plant sheet forming problems, but we also do training. I've written about 100 articles for Science Metal Forming magazine under the Science of Forming or the Metal Matters columns. I'm the technical editor of the Advanced High Strength Steel Application Guidelines, and I'm also the lead content creator and presenter on metallurgy and formability items for World Auto Steel Partnership, and the Precision Metal Forming Association. But that's me. Let's talk about the potential issues that you're facing. What are the things that might influence stamping success? The bottom line performance comes down to stamping success. What are the things that would affect that? Well, it's the chemistry and the microstructure of the product that you get, as well as the processing that occurred in the sheet mill, be it steel, stainless, aluminum, copper, and so on. Those processes that are used affects the performance. But in addition to the sheet mill, it's also what happens at the service center or even within your own facility. The act of unwinding a coil changes the strain state within the product. And those can have an impact on the performance and through the material properties that come out, not just the material properties that are measured at the sheet mill, but also the properties and how the property changes as going through this processing. What are the properties that we're talking about that could affect performance? Well, it's grain size, inclusions, residual stresses. Don't forget about the surface. The surface profile affects how metal is flowing in your stamping operations. And then there are the properties that come out of tensile testing, as listed here, as well as the forming limit curve of the material. We'll be talking about that. It's not a commonly measured parameter, but it really has a great influence on your stamping success. What are we talking about this morning? Well, it's going to be the properties that are highlighted in yellow. So the properties fall into three main categories: the hardness, the strength, and the ductility. Hardness is simply a measurement of the resistance to permanent indentation. Best thing about it, it's quick and easy. It is great if you're looking to assess if your stamping tool, your stamping dies have had the proper heat treatment. That is an absolutely perfect application for hardness testing. Unfortunately, it is test procedure dependent, and it's a really poor indicator of formability. Why do I say that? Because of what Rockwell testing is. As I said, or any other type of hardness test, it's a resistance to indentation. It is determined by pressing a 16th inch diameter ball, if we're talking about a Rockwell B scale, into the metal, and we're just measuring the depth of that indentation. It drops into a formula. This is all happening behind the scenes, that you're not actually doing the measurement. It's built into the equipment. The implications of this is that if you're looking at a reading of a Rockwell B80, you're talking about 4 thou of penetration. If you're talking about a Rockwell B40, it's 7 thou penetration. Or breaking it down further, each Rockwell point is the difference between a tenth of a thousandth of an inch of penetration. So if you're saying that you need no more than a Rockwell 60 to form this part, and you're saying, great, a Rockwell 59, fantastic, but a Rockwell 61, nah, sorry, we're going to need to reject this coil. We're talking about the difference in penetration of 4 microns. Relative number as to what 4 microns are, you could look at it relative to the human hair, which is roughly 100 microns, or your cornea, which is about 500 microns. So is the equipment you're using for Rockwell testing sensitive enough to measure to the micron layer? Well, possibly, but even so, your metal forming process is not an indentation process. What you should be using is tensile testing. Tensile testing is just a schematic. You could do it on a flat sheet, which is what we're talking about today, just sheet metal products, but you can also do it on tubes or round specimens and so on. What do we get out of a tensile test? It is stress and strain. What is stress? It is force divided by the cross-sectional area. In the tensile machine, we grip at the top, we grip at the bottom. That's what these outer portions are for gripping the sample, and we pull it apart. And what gets measured in a tensile test is stress, measured as force divided by the cross-sectional area, as well as strain, which is looking at the gauge region, which is where we have our extensometer as an example, or we focus our DIC pattern if you're doing non-contact approach. And it's the section that we're measuring. Everything else in terms of measuring the stress and strain is ignored. We're just looking at the gauge region, which for an ASTM tensile bar is 12.7 millimeters across and 50 millimeters A to C or B to D. The strain is the change in length relative to this original length. And that's all we're measuring out of a standard standard tensile test. And from that, we plot stress on the vertical axis, strain on the horizontal axis. And this general shape of the stress strain curve is typical for all metals, where we start off with an initial linear section, then it starts curving and is nonlinear, reaches a peak, and then drops off from there. What's the information we can get out of the stress strain test? First is the modulus of elasticity, or Young's modulus, or sometimes called the E modulus. And that is simply the slope of this initial linear portion. That slope is roughly going to be 30 million PSI for steel grades and 10 million PSI for aluminum grades. That difference in the slope has very significant influence on the spring back of your formed part or your dimensional accuracy. The spring back that you're going to get is inversely correlated with the modulus. So steel has a 3 times the modulus of aluminum. That means that steel products are 3 times as stiff as a comparable thickness part made out of aluminum. And you're going to have
The remaining 35 minutes of the video is available at the URL shown here. The URL is also shown in the description for this video. The video is a continuation of what you've been learning here, covers the tensile properties found on metal certs, the important tensile properties that aren't typically shown on metal certs, the tensile properties to focus on for improving forming success, and an approach that provides insight on where problems are likely to occur during metal stamping. If you have any questions, feel free to email or to call at the phone number and email shown here.